Hi there. So in this section 2.5, this is called a preview of composite and inverse functions. So I'm going to talk to you about composite and inverse functions and show you a bit of the mechanics, and then we'll do a bunch of different examples. Okay, we will be reinforcing these later. I do want to say that, number one. And number two, as we build up our cache of functions, different types of functions, I'm going to keep coming back to these ideas, okay? Because it's kind of hard to talk about composite and inverse functions when we haven't developed too many of them yet. So as we develop more functions, we'll come back and reinforce this. So we've got composite and inverse functions. All right, so the first thing I'm going to talk about is our composite functions, or we can call it composition of functions. Okay, I'm first going to just do the mechanics, and then we'll get a little bigger and talk about how we can do these things with word problems. Okay, so the way I think of composite functions is I think of an assembly line. Okay, so what happens in an assembly line? Well, someone starts with something here, they do something to it, and then something comes out. Okay, so this is what their input is, they do whatever their job is, and something comes out. And then the next person takes what came out and does something to it. Okay, so think of it like this. Okay, let's pretend that our input is our bare foot. Okay, well, then our first function could be putting on a sock. So the input was a bare foot. The function is putting on a sock, and out comes a socked foot. Now, what do we do with our socked foot? Well, we can put on a shoe. So again, you can think of a bare foot here, a foot with a sock, and then the next function is to take the foot with the sock on it and put on a shoe. Could you go the other way? In other words, could you put on your shoe first and then your sock? Yeah, I don't know why you'd want to, but we could do this. So essentially what we're doing is we're starting with some value and we're applying a function to it. Okay? Let's suppose our first function is f and our second function is g. Well, how do we write what comes out of this function? Well, can't we write that our output is f of x, right? X, we plug x into our function f, and this is what comes out. Well, now what happens? We're going to take this value and we're going to plug it in our function g. So what does that look like? Well, we're taking our function g, and what are we plugging in? We're plugging in f of x. Okay? In a similar manner, we could start out with a value of x, and we could first plug it in our function g. What are we doing? We're taking x, and we're plugging it into g. And then we could plug that into our function f. What does it mean to plug this into our function f? Well, we've got our function f, and in it, we're plugging in this output g of x. Okay, this is what it looks like notation-wise with our composition of functions. Now, we could write this as g composed with f of x, but once I see that, I always just automatically write it g of f of x. And in a similar manner, we could say this is f composed with g of x. Okay? The point is this. If you see something like this, immediately you want to think, oh, that's g of f of x. Just like with your order of operations that you've done in your past, you always work inside out. That's the same thing here. Notice we're starting with x. We're plugging it in our function f, And then we're plugging that whole mess into our function g. And in a similar way, notice that those order of operations go here too. We start with x. What's the first function we plug them into? G. And then we take that and plug it into our function f. So to show you how this works in practice, I'm going to start out with just a couple of examples with numbers, and then we'll build up. Okay? So I'm just going to randomly pick a couple of different functions and go with it. So let's suppose we have a function f of x is, say, 2x plus 3, and let's let g of x be x squared minus 1. Where'd those come from? The top of my head. Okay? So what if I wanted us to compute, let's do f of g of 3, and then let's do g of f of 3, and we'll do some more examples. Okay? So what do we do here? Let's start with this top example. We start with 3. What function do we plug them into first? We plug them into our function g. So over here we can do side work. We need to know what is g of 3. And if you want me to draw that whole long diagram, we can do that too. Well, what does it mean to compute g of 3? Everywhere where we see an x in our function g, we're going to plug in 3. We get 3 squared minus 1, which is 8. All right, so we found that g of 3 is the same as 8. So isn't this now equivalent to computing f of 8? It is. So now we're going to plug 8 into our function f. So we're going to look at f of 8. Well, that's 2 times 8 plus 3, or 19. So the answer to this guy is 19. On the other hand, the bottom guy. Now we're starting with 3 and we want to plug them in f, and then we'll take that output and plug them in g. So the first thing we need to do, again we work inside out, is compute f of 3. Well, so we're going to take 3 and plug them into f. So we get 2 times 3 plus 3, which is 9. Again, we see that f of 3 is equal to 9, so now we're going to be computing g of 9. So g of 9 is 9 squared minus 1, or 80. Isn't that cute? I just love this. Okay, well, let's do a couple more with numbers. What if now I want to find f of g, let's make life nice for ourselves, of 0, and then we're going to do g of f of negative 1. Okay. Well, how do we do this? This first guy, we're going to compute g of 0 first. Okay? What is g of 0? Well, that's 0 squared minus 1, or negative 1. So we found that g of 0 is negative 1, so I'm going to replace g of 0 with negative 1. And now we need to compute f of negative 1. So that's 2 times negative 1 plus 3. And out comes positive 1. How do we do this guy? Well, the first thing we're going to do is compute f of negative 1. Oh, fun! Well, that's 2 times negative 1 plus 3. Why did I say fun? Because we just computed that, and we get 1. So, since f of negative 1 is equal to 1, I'm going to replace f of negative 1 with 1. And what is g of 1? Well, that's 1 squared minus 1, which is 0. Oh, that was cute. Okay, now, one other thing that you will have to be able to do is not only compute this at various values, but we're going to also want to compute this in general. Okay? Now, I'll show you how that works. We're going to follow the same basic steps, and we'll work through this example here. Okay? Now, one way is going to be easier than the other way. That's not always the case, but it is typically the case. Okay, I'm going to start out with the easier way first. And easy, of course, guys, is a relative term. Okay, so what does it mean to do in general f of g of x? And then over here, we're going to do g of f of x. The same idea follows for both of these guys. When I say harder or easier, it's more just which is more work. Okay? We'll do the least work one first. All right. So if we follow what we've been doing, we look at this and we say, okay, we're starting with x and we want to plug them in g. Well, there's no number to plug in. So what you do in these general situations is you just replace the whole inside. Do we know what g of x is? Well, in this particular example, we do. It's x squared minus 1. So we write that function inside. Okay, all I did is say, oh, in this example, g of x is x squared minus 1. Now, what does it mean to compute f of x squared minus 1? Everywhere where we see an x in our function f, we're going to plug in x squared minus 1. So 2, we see an x, we plug in x squared minus 1, and then plus 3. This is why we were playing with plugging in values so much earlier on. All right, well, we can simplify this, distribute our 2, and then combine like terms, and we're going to get 2x squared plus 1. All right, what if we want to go the other way? Well, again, we work inside out. We know what f of x is in this example. It's 2x plus 3. So we're going to replace f of x with that 2x plus 3. Okay, now what does it mean to compute g of 2x plus 3? Means everywhere where we see an x in our function g, we're going to plug in 2x plus 3. So we have 2x plus 3 quantity squared minus 1. Okay, why is this more work? Because we actually have to go through and simplify this. Okay, how do you multiply out 2x plus 3 quantity squared? I always think of that as FOIL. Remember the first, outside, inside, last? Okay, so first term's 2x times 2x is 4x squared. Notice my outside terms give a plus 6x. My inside terms give a plus 6x, so I have plus 12x. And then my last terms give me a 9. And then don't forget to subtract 1 at the end because that's what's indicated in my function g. So when all is said and done, we get 4x squared plus 12x plus 8. And that's our final answer. I understand a lot of times in math people don't know when to stop. Okay? Don't set this equal to 0 and factor and solve. That's not what we're doing here. We just wanted to find the composition of functions. All right, so those are our basic mechanics with the compositions. What I would like to do is just an example of a word problem. Alrighty, so essentially when do you use compositions of functions when you have word problems? Essentially you use them when the output of one function is the input for another function. Okay? So what's an example? Well, I claim that, for example, the cost to paint a room depends upon the number of gallons of paint needed. But I claim that, I claim that the number of gallons of paint needed depends upon the square footage of the room you're going to paint. So it depends upon the area of the room. So we could say that the cost is a function of the number of gallons needed, but the number of gallons needed is a function of the area. Okay? So that's how we can look at these things. So what's an example that you might see? Let's do one. All right, so what we're given here is we have R of F of P, and it says where Q, which is F of P, is the number of barrels of oil sold by a company sold at price P. And then we say that, I hate how this book throws in so many different things. R of Q, I would just keep it as F of P, is the revenue in millions from a sale of Q barrels. And all they want us to do here is give the units and the meaning of this. Okay? So essentially what they're saying is that F of P is the number of barrels of oil sold at a price P, because certainly the number of barrels sold is going to be a function of the price. Okay? And then what we're saying is the revenue at F of P, okay, is, well, it's the revenue of when we sell those Q barrels. So the way that I would write this in words is I would always start with my outer function, this R, what those units are. That R is the revenue. Okay? Well, what is it the revenue of? I will say in millions of dollars. Well, essentially what you can do is just jump to the inner unit at a price of P dollars per barrel. So when you're trying to put these things in words, start with the units of the outer and then jump to the very inner. All right. So those are our basics with our composition of functions at this point. What I would now like us to do is talk a little bit about inverse functions. Now, really, inverse functions get a heck of a lot more interesting once we've built up our cache of functions. But let me just talk a little bit about what the meaning of an inverse function is. Okay? An inverse function essentially undoes what your original function does. So if your function is to open a door, your inverse is to close it. You get back to where you started. Okay? Let's pretend I start with a bare foot. Okay? If my function is to put on my shoe, my inverse function is to take it off. In other words, I'm back with my bare foot. Okay? So the key thing to remember with your inverse functions is they undo your original function. Now there's a lot to say here with inverse functions. So for example, if my function takes 1 to say 5, my inverse is going to take 5 and bring him right back to where I started. Okay, it's just undoing it. Our notation for inverse functions is essentially f to the negative 1 power. Okay? Now, a couple things to point out. If I look at these as ordered pairs, do you agree that my function f is taking the input of 1 to the output of 5? We could write that as an ordered pair. What is my inverse function doing? Well, now my input is 5, and it's taking it back to 1. This happens essentially all the time with your inverse functions. If your function takes, say, a to b, then you automatically know the corresponding ordered pair on your inverse. It takes b back to a. Notice your x and y values are just switched. Why does this make sense? Well, in general, look at this. Here's the domain of my function f, and that goes to the range of my function f. But if I want to look at my inverse, well, that's exactly what my input is for my inverse. So that's the domain of my inverse, and this is the range of my inverse. So, one important thing to notice is that the domain of your function is the range of your inverse, and the range of your function is the domain of your inverse. Okay? So, that is number one with these functions. Now, let's think about this, okay? One question we have to ask is, well, there's actually 3 questions we're going to ask. The first question is, when do inverses exist? Do inverse functions exist for all functions or just in some cases? That's one really important question. The next important question is, if an inverse does exist, can we find the formula for it? And then the third and final question is, if we're given 2 functions, how can we verify whether or not they're inverses of each other? Okay? So let's do this one by one. So our first question is, when do inverse functions exist? Okay? Well, I could just answer it, but let me motivate the answer a little bit. Okay? Let's pretend we have a function f, and f takes 1 to 2, 2 to 3, and 3 to 4. And then let's pretend we have a function g. G takes 1 to 2, it takes 2 to 3, and it takes 3 to 3. I claim that both of these are functions. Remember, in order to have a function, each input, each value of x goes to exactly one value of y. Okay? 1 is only going to one place, 2 is only going to one place, and 3 is only going to one place. Okay? Given these, okay, if my function takes 1 to 2, wouldn't you grant me that my inverse would take 2 back to 1? So then we're back where we started. If my function takes 2 to 3, my inverse takes 3 back to 2. And if my function takes 3 to 4, my inverse is going to take 4 back to 3. All right, life is pretty chill right there. Okay, so we have a function and we have an inverse. Notice this inverse is totally legit as a function because 2 is only going to one place, 3 is only going to one place, and 4 is only going to one place. Okay, now let's look at g. Well, what happens here? If my function g takes 1 to 2, won't g inverse take 2 back to 1? If my function takes 2 to 3, won't my inverse take 3 back to 2? And similarly, if my function takes 3 to 3, won't my inverse take 3 back to 3? I claim we got some problems here. What is the matter with this guy? I claim he is not a function. Why? Because notice I have an x value going to more than one y value. Okay? So, what the difference is the following. Okay? In order for a function to have an inverse, the function must be what we call 1-to-1. And if it's not 1-to-1, and don't worry, I'll define that in a second. If it's not 1-to-1, don't worry, we can restrict our domain so that it is. Let me show you in a picture, okay? So, one of my favorite functions to play with in this class is y equals x squared. And we were playing with that last time when we were doing the shifts. Okay? So here's the ordered pair 1, 1, and remember this takes negative 1 to 1. Okay? This is totally a function. Remember, in order to have a function, it has to pass your vertical line test. Okay? And this is certainly a function. Notice we could say this takes 1 to 1 and it takes negative 1 to 1. But I claim he does not have an inverse function. Why? Because if this is our function, wouldn't the inverse, well, it would take 1 back to 1 and it would take 1 back to negative 1 and he's no longer a function anymore. Okay? So in order for a function, in order to have a function, each x value can only go to exactly one y value. In order for your function to be 1-to-1, each y value can only be quote-unquote hit by one x value. So everyone gets a partner and only one partner. Now, the best way to check whether or not your function is 1-to-1 is with your horizontal line test. Notice, since this horizontal line passes through more than one point, he is not 1-to-1. So your horizontal line test is essentially equivalent to your vertical line test. It just tests 1-to-1-ness. Okay? So, in order to tell whether or not a function is going to have an inverse, it needs to be a 1-to-1 function. What do we typically do here because we want to have an inverse? We typically just then restrict the domain. So we would say, oh, well, let's just deal with values of x greater than or equal to 0, and this portion here is 1-to-1, and then we're satisfied. Okay, so when do inverse functions exist? When they're 1-to-1. Essentially, do the horizontal line test. Honestly, I won't ask you to find the equation for a function's inverse unless it is a 1-to-1 function. Okay? Alrighty. Next, our second question. Our second question is how to find the inverse. Now, we will be building up more types of functions that we can find inverses of, but let's just start here with these functions that we already have. Okay? So, what is an example of someone we might want to find the inverse of? I'm going to write an example down, and then I'll tell you how to do it. Okay? So suppose we have our function 3x minus 7. I think you guys will grant me this is a line with a y-intercept of -7 and a slope of 3. It looks something like this. This is certainly a one-to-one function. It passes a horizontal line test because any horizontal line drawn passes through at most one point. So, how do we find the inverse of this function? In other words, how do we figure out what undoes this function? Well, remember the relationship. You're really just switching your x and your y values. So in order to find the inverse, okay, I'm assuming that we just have x, y. You can play with the variables as they change. But what I will tell you is the following. What you'll want to do is switch your x and y values and then solve for y. And I claim that this actually will give us our inverse. So, step 1, switch your x and y. That's the easy step, okay? So I say x is 3y minus 7. My next step is now to solve for y. Sometimes this can be a real pain, trust me. I claim in this example, it's not too bad. Okay, how do we solve for y? Well, the first thing we would do is add 7. So I have x plus 7 is equal to 3y. And now to get y alone, I divide both sides by 3. So I could say y is x plus 7 over 3. And we got it. Another way to write this is 1/3 x plus 7/3. And that's our first example. Okay, now what's another example we can look at? All right, let's take this guy. What if now I'm giving us, okay, f of x is x cubed plus 2. I claim he's a one-to-one function, okay? I know my basic graph of y equals x cubed. I always call that my John Travolta function after a really bad movie. But anyway, look, if this is your graph of x cubed, what do you do when you add 2 at the end? Don't you just take that whole graph and move them up 2? Yeah. So, anyhow, side matter. I claim this is totally a one-to-one function. First thing that I would do is in place of f of x, I would write that as y. My next step is to switch my x and y. So I get x is y cubed plus 2. And now I solve for y. First thing I would do is subtract 2. So I have x minus 2 is y cubed. Now, we don't want y cubed, we want y. How do you undo cubing something? You take the cube root of both sides. So we get y is the cube root of x minus 2. Or we could write that, since my original function was given f of x, f inverse is the cube root of x minus 2. Okay. So, that's question 1. That's question 2. The third question is, how do we know if our two functions are inverses? So our third question is how to verify that they're actually inverses. Okay? This is fun. So check this out. Okay? Remember how I told you guys that if our function, say, takes 1 to 5, our inverse takes 5 back to 1? Look how I wrote this. Notice, I wrote this as a composite function. Okay? In other words, you have an inverse function if, here, let me do it this way first. Okay? Let's see what happens. If we start with some value of x, who cares what it is, and we plug them in our function, something's going to come out, right? Well, this something that came out, we want to plug into our inverse, and we want to get back to where we started. Okay, watch this. We start with a value of x, we plug them in our function, and we get f of x. If these guys are indeed inverse functions, then when I plug f of x into my inverse, I have to get back to where I started. And in fact, this has to go both ways. In other words, f of g of x has to be x, and g of f of x has to be x, if in fact they're inverses. So let's actually just take these guys right here, okay? Didn't we find, let's just call this g of x, didn't we find that g inverse was x plus 7 over 3? Let's verify that these two are inverses of each other. Okay? Well, we need to compute g of g inverse of x, and we need to compute g inverse of g of x. All right. Well, how are we going to do this? This is just reinforcing our composition of functions. Right here, what we do is we say, well, g inverse, you plug in your entire function, is x plus 7 over 3. Right? You just plug in whatever that inverse function is. Alrighty. Well, what does it mean to compute g of x plus 7 over 3? Everywhere where we see an x in our function g, we're going to plug in x plus 7 over 3. Well, let's do it. What happens here? Don't those cancel? And we're left with x plus 7 minus 7, which is x. So cool. And we can go the other way too. Here, what we do is we say, well, what is g of x? Oh, g of x is 3x minus 7. And now we want to compute g inverse of that. In other words, everywhere where we see an x here, we're going to plug in 3x minus 7. Well, doesn't that look like 3x minus 7? That's what we plugged in for x. Then we have plus 7 over 3. Well, minus 7 plus 7 cancels, and 3x over 3 is x. All right. Let's do that with this one here. And then we just have a few word problems to go through. So here we found the inverse to be the cube root of x minus 2. So what we're going to do right now is just verify that these two are inverses of each other. Okay? So let's do f of f inverse of x. Well, we start on the inside and we're given that f inverse is the cube root of x minus 2. Looks like a really nasty thing to initially have to plug in, doesn't it? Alrighty, well, let's see what happens here. What does it mean to compute f of this cube root? Everywhere where we see an x, we're going to plug in this shipwreck. So don't we have the cube root of x minus 2 cubed plus 2? Well, remember, cubing your cube root, they cancel each other out. So you're left with x minus 2 plus 2, which is simply x. And in a similar manner, if we want to do f inverse of f of x, well, now we're going to compute f inverse. F of x here is x cubed plus 2. So what does it mean to compute f inverse of this? We plug this in for x. Don't we have the cube root? Well, in place of x, I'm going to put x cubed plus 2, and then we got that minus 2. Those guys cancel. You're left with the cube root of x cubed, which again is x. All right, let's just do a couple of word problems just to reinforce this. I know this is a lot of information, and actually inverse functions are probably one of the most important things we talk about. And I will again keep reinforcing all of these ideas, I promise you, as we move forward. Okay, so first let's just start with this. All we want to do with this example is give the meaning and the units of the inverse function. Okay, so let's suppose P equals f of t. Suppose that's our population in year t. Okay? All right, so do you agree that essentially we have t going to p? So this is the year, and this is our population. This is our function f. Okay, so f inverse, won't that take p to t? Now my input is population, and my output is the year. Okay, so how do we write what the meaning of that is? Well, let's first talk about how we write the meaning of this. Notice, when we described this function, I started describing it by using the units of my output. It's my population in year t. So when we describe these things, we start with the units of our output in terms of then the units of our input. So our output is the year, okay? Well, the year at which we have a population P. Just like this is the population in the year T, this is the year at which we have population P. I know that it's funky. Okay? All right, one more example of a word problem here. And this is as follows. The cost in thousands of dollars. Where am I? Oh, here we are. Of producing Q kilograms of a chemical is given like this. Okay? So, all I want us to do is describe in words what F inverse, say, of 200 is, and in general, what F inverse of C is. Okay? Notice we can't really compute anything because we're not actually given a function. But again, we can interpret these things. So let's notice our function is taking Q to C. In other words, kilograms to the cost in thousands. So won't my inverse take C back to Q? Yes. Remember, they switch. Okay? So it doesn't really matter which order we do, but notice this is the cost in thousands and it's in kilograms. I'm going to do my general one first. Okay? Now, again, how do we interpret this in words? Start with your output. Okay? So the way we would start with our output, notice here it was the cost to produce this many kilograms. Okay? Now what we have is, this is what? Start with your output. The number of kilograms, we could say, of chemical needed, what? At a cost of C, thousands of dollars. Okay? So specifically, then, if we wanted to interpret what F inverse of 200 is again, it's the number of kilograms of our chemical, that's the output of this guy, needed to be produced at a cost of, well, $200,000. Okay, we will practice this more because I definitely get that this is kind of a funny little idea. There's one more example I would like to do. It's not a word problem, it's just a graph, and then that will conclude this section. Okay? So, let me just draw a simple graph here, just to kind of summarize these inverse functions in terms of looking at a graph. All right, so this is 1.5 and this is 2.2. And this is my function f of x. And what I want us to find is the following. F of 0, F inverse of 0, F of what equals 0, and F inverse of what equals 0. So we want to replace our question marks. Okay, this is fun. First off, both of these are ordered pairs. This is 2.2 comma 0 and 0 comma 1.5. It's crucial that you know those, okay? And these are both on my function f, right? So my function f takes 0 to 1.5, and doesn't it take 2.2 to 0? Why am I writing it like this? Because I claim it'll help us answer our questions. Using the idea of an inverse, won't my inverse take 1.5 back to 0? And won't my inverse take 0 back to 2.2? And that way we get back to where we started. Okay? So if I wrote this as an ordered pair, wouldn't that be 1.5 comma 0? And then 0 comma 2.2? Notice my ordered pairs are just switched. I claim we can do this. Okay? What is f of 0? Well, f of 0 is 1.5. Now they're asking f of what is 0? In other words, we got question mark, comma, 0. Well, that's 2.2. Now if we want f inverse of 0, notice 0's our input. Well, when 0's the input of the inverse, we see that 2.2 comes out. And here, what we're asking for again is, well, f inverse takes what to 0? Well, we see we have 0 as an output there, so it's 1.5 here. All right, I hope that gets you started in a good way on this section. Thank you.